Hi everyone, thank you so much for clicking on to the video. Today we're going to be looking at combined techniques. So we're going to look at the deduction of the structures of organic compounds from different analytical data, including elemental analysis, mass spectra, and infrared spectra. So now we're going to look at combined techniques. We can use a combination of techniques to identify organic compounds and determine their structures. And so firstly, we can use elemental analysis. So this allows us to obtain the empirical formula of a compound using percentage composition data. And then secondly, we have mass spectrometry, which allows us to determine the accurate relative molecular mass of a compound and also the fragmentation patterns produced can suggest to us possible groups present. And then thirdly, we have infrared spectroscopy, and this allows us to identify particular functional groups in an organic compound. So now we're going to look at a quick example of how we could combine these three techniques. So an analytical chemist was provided with a compound with an unbranched carbon skeleton. The compound is made up of 70.59% of carbon, 13.72% of hydrogen, and 15.69% of oxygen. In its infrared spectrum, there was a broad absorption at 3,550 centimeters to the minus 1, and in its mass spectrum, the molecular ion peak was located at an MZ value of 102. Use all of the information to suggest all the different possible structures for this compound. So firstly, I'll work with the percentage composition data first. So we're going to look at working out the empirical formula. So we do this in exactly the same way as we normally would. So we set it out as carbon and then hydrogen and then oxygen. How I know it's only made up of these three elements is because if we add up all the percentages that were given, they equal 100. So again, I put the percentages below each element. So we've got 13.72% of hydrogen and then 15.69% of oxygen. And so the first step is to divide by the AR. So we have 70.59 divided by 12.0, and this gives us 5.88. And then we have 13.72 divided by 1.0, which is equal to 13.72. Then finally we have 15.69 divided by 16.0, which is equal to 0.98. So here we've divided by all of the ARs. And then the second step is to divide by the smallest. So the smallest is this 0.98. So we have 5.88 over 0.98, which is equal to 6, and then 13.72 divided by 0.98 is equal to 14, and then finally 0.98 divided by 0.98 is equal to 1. So here we've divided by the smallest, and so now we have our ratio. So the ratio is equal to 6 to 14 to 1. And so this gives us our empirical formula. So the empirical formula is equal to C6H14O. And now we can look at the information we've been given about the mass spectrum to work out the molecular formula of this compound. So we're told that we have a molecular ion peak at an MZ value of 102. And wherever the molecular ion peak is, this is actually the MR of the compound. So we have that the MR is 102. So from the mass spectrum, we've gained the information that the MR of this compound is equal to 102. And so now we can find our molecular formula of this compound, because we find the unit of the empirical formula and then multiply this unit by all of the different, by the empirical formula. So we have the unit of this empirical formula is equal to the MR of the compound, so 102.0, over the MR of the empirical formula. So we have 6 of these carbons, and then 14 of these hydrogens, and then also 1 oxygen. And this actually gives us 1. And so that means that the empirical formula is actually equal to the molecular formula. So we have that the molecular formula is equal to C6H14O. And finally, now we can look at the infrared spectrum to work out what kind of compound this is. So in the question it said that there was a broad absorption at 3,550 centimeters to the minus 1. So all we need to do is look at our data booklet to find what this value corresponds to. So we have infrared absorption at 3,550 wave numbers. This tells us that this is actually an alcohol. So we have this OH group. And this makes sense looking at the molecular formula because we have 1 oxygen. And so the compound has to be an alcohol. And it's also unbranched because I told that in the question. So we just need to focus on where we put this alcohol group. So the first structure we could have would just be 6 carbons in a chain, and then the OH at the end. And then obviously we have hydrogens everywhere else. So what we formed here is hexanol, hexan 1-ol, because we have the OH group on the first carbon. It could also be carbons in a chain again, but this time with the OH on the second carbon, and hydrogens everywhere else. So this is hexan 2-ol. And then finally we could have hexan 3-ol, so this time with the OH in the middle. So again we have this unbranched chain of carbons, and then this time we have an OH on this third carbon. So this is hexan 3-ol. And you might think that we could also put an OH here or here, but actually these are the same as hexan 2-ol and hexan 3-ol if we flip the molecule over. And so these are actually our only possible structures.